Hello and welcome to part 4 of the video series Introduction to Convolutional Neural Networks. In previous parts, we basically discussed some of the terminology related to convolutional neural networks and also some of the motivations why convolutional neural networks, they are actually important in solving a lot of computer vision kind of problems. But we also discussed that these are not just the images that the convolutional neural networks are best for. They can be extended to other structural inputs and other structural data as well. In this particular part, we are going to basically look into the details of some of the operations in convolutional neural networks. And basically, we will be diving in to see some of the very low level details of how the convolutions and how the poolings, they actually different convolutional layers and pooling layers, they actually are implemented. So the goal for this particular part is to introduce you the very low level details of the implementation of these different layers, convolutional layers and pooling layers. And in the subsequent parts as well, we will be basically driving the backpropagation algorithm for convolutional neural networks that sometimes is considered a relatively complicated task for CNNs. Although the backpropagation for normal or plain neural networks is somewhat easier, but I will try my best in this video and in the subsequent videos to make the backpropagation in convolutional neural networks as clear as possible by taking a help of a very simple example. The implementation that we will be seeing will be involving a lot of for loops. I will not be driving that I will not be driving in terms of vectorized implementation that I personally think somewhat confusing. Sometimes it becomes confusing for the beginner to understand the vectorized operations. Rather, I'll be actually driving each and everything index-based, and you'll be seeing nested loops and stuff like so. The details of the implementation. Although in different languages like Python and other languages, the implementation is really vectorized, and that is the implementation that one should actually go for when implementing these kind of things, because that is really fast. But it turns out that starting from the very beginning with vectorized implementation may confuse a lot of beginners. So I plan in this video series to basically, from here onwards, I plan basically to give you low-level details with index-wise operations rather than vectorized operations. And going through the example, you'll be actually prepared for driving backpropagation for convolutional neural networks for arbitrary large networks, although the example we will see will be really small and simple, but that can be extended to larger networks. So let's dive into some of the details of convolutions and poolings and backpropagation. So before actually diving into the details of convolutions and poolings and backpropagation and all that stuff, it is important to just get a recap of the general architecture of a convolutional neural network. So assume, for example, you have an RGB image, let's say. Let me draw the channels in the same color as they should appear in order. So RG, and then let me draw the blue here. So let's say that's image. Assume that the image has height as m number of rows, and let's say n number of columns. And in this particular case, the number of channels of the image in this particular case is basically 3. So 3 channels. Now assume that the very first layer you decided to have, for example, a 5x5 filter, convolutional filter, let's say 5x5 filter. So if you have a 5x5 filter, it must also be a 5x5x3 matrix at the end of the day. So 5x5x3, so 5x5x3, and you can have several such filters. Maybe let's say you have, for example, 10 such filters, or maybe you can have several of those. Now, when you will convolve the very first filter with the image, assuming that you zero pad your image, the result for the very first filter will be if the padding is the same, the very first filter will result a m by n mask or m by n result of the first convolution. Then the second filter will also result in an m by n response, and so on, and you will be having basically 10 of those. So we can write these 10 matrices as a volume, obviously, like this is the response of the very first filter, and that is the response of the second filter, that is response of the third filter, down to response of the last filter, which is 10. So in that case, the output of this convolutional layer will basically be, if the padding is the same, if we zero pad so that the output stays the same, that will be m by n by 10. So then what we do is we actually pass each and every value of every channel through a nonlinearity like ReLU or something else. ReLU is mostly used. We pass that through ReLU, but before passing this structure, which is m by n by 10, we actually add biases for different channels as well. So for example, this filter has its own bias. Let me call that as B1. This filter has its own bias. Let me call it B2. And we have 10 such biases. So we basically add bias to the first channel. We add bias value, same number to the second channel, then the same number to the third channel, and so on. So let me have this bias vector. We add that to every channel or bias matrix of the same size. And then we apply nonlinearity. And the result again is the activations of the very first layer, which is m by n by 10. So this is the convolutional part of the first layer. Then what happens is normally we apply the pooling, let's say max pooling. Let's say the size of max pooling is let's say 2 by 2. Then what happens is for the very first channel, we pick a 2 by 2 window, we find the max of it, and we place that in the very first output here. Then we pick the second window. Maybe the stride normally is taken as non-overlapping, but you can take a stride as well. Here in this particular example, let's say we have no stride in pooling. So that's the maximum value, So once the first channel is gone, the size of the resultant size will be m by 2 and n by 2. And the same max pooling will go on the second channel, and same max pooling will go on the third channel, and so on down to the 10 channels. So the result eventually will be, m by 2 by n by 2 by 10. So this sometimes is called one layer, although you might be thinking a lot of operations that is going on. But this convolutional layer followed by a pooling, max pooling, or some other pooling method as well, mostly max pooling is used. That combination is called one convolutional layer. But normally the general architecture of, and then obviously this serves as the input for the next convolutional layer and so on. But what happens, what can happen in general architecture of convolutional neural network is you need not to follow the convolutional layer, the convolutional operations always with the pooling operation, and then convolution, then pooling, and you need not to follow that, although most of the practitioners, they follow this kind of sequence. Sometimes people come up with, for example, some of the convolutional operations. So for example, C1, C2, C3, and then apply first pooling, and then some of the convolutional operations, for example, C4, C5, and then another pooling, and so on. The common convention also is that after each convolution, you pass the result of the convolution through a nonlinearity, and then you pool the value of the, so the result of convolutions is the activations, and then you pool the activations. And this is uncommon, however, that you actually pool first and then apply the nonlinearity. Although the earlier versions of the very earlier versions of convolutional neural networks, they actually apply activations after pooling, but now the convention is to apply pooling after convolution, apply activations after convolution, and then apply pooling. So, so in general, you can have a convolutional neural network with any kind of sequence of these operations. You can have any kind of activations for different layers, or maybe same for all layers. You can have any number of filters at any layer. You can have stride parameters, whether you are going to add padding or not going to add padding. What is the stride parameter for convolution? What is the stride parameter for pooling? And you have to decide all these things. And any of these combination will give you a convolutional neural network. And that might be best for your data set at hand or not. That's another question. But either way, you can define a convolutional neural network with any of these kind of combinations. So that's about the general architecture of convolutional neural network. So next we will see that next we will take an example of a very simple convolutional neural network with just one convolutional layer and a squared error term, and we'll try to drive the details of convolutions and max poolings and try to write code in terms of low-level code in Python for convolutions and max poolings. And later on, we will also see how to basically get the derivatives and apply backpropagation on that. So let's take a concrete example let's take a concrete example to actually drive out all the details. And let's take an example that is really simple. So for example, let's say we are going to build a convolutional neural network which works on, let's say, grayscale images, let's say, and the image is, let's say, 32 by 32. That's our input image. Let's say I, that's our input image. And let's say the convolutional layer actually has two convolutional filters. One filter is, so both filters are 5 by 5. So that's filter 1. Let me call that as K1, which is a 5 by 5 filter. And let's say we have another filter, which is K2. That is also, again, 5 by 5 filter. And what happens is the image actually get convolved with this filter and results basically a map. Let me call that map as C1. Let me call that map as C1. And assuming the same padding, which means the output is also the same as the input, this map of this map is also 32 by 32 in this particular case. And then basically what happens is we convolve our image with this particular mask as well, convolutional filter as well. And then the result we get, let me call that result as C2, the output of this kernel or convolutional mask. And that is also 32 by 32, assuming we have padded everything here. Here we must note that this C1 is basically achieved. So C1 is basically achieved after applying the convolutional filter. And after applying convolutional filter, we actually add a bias P1. And whatever that result is, we apply a ReLU on that. So let's say we have ReLU nonlinearity. So what we actually did is the following. So let me write what actually C1 represents. Every value of this C1 is actually the result of convolution plus a bias, and then ReLU nonlinearity is applied on that. So this is basically the activation. So we can call this activation as ReLU applied on the output of the kernel plus bias 1. So that is this particular value. Similarly, we have bias 2 here for this particular kernel, and nonlinearity, again, we are thinking about ReLU, just to take things simple. Although later on we can generalize all these kind of things. to other nonlinearities, to many number of channels and stuff like so. Then what happens is basically we apply a max pool on C1 and we convert that. So let's apply 2 by 2 max pool, and C1 is converted to, let's say, S1. So the value of S1, the dimensions of S1 in this particular case is 16 by 16. Let's say we apply a stride of 1 and stride of 2, which means non-overlapping, and we come up with this 16 by 16 mask. And again we apply max pooling here as well, and we get S2, which is again 16 by 16. So then what we do is we actually flatten out the result of this matrix, which is basically 16 square vector, and we flatten out the result of this S2 as well, which is again 16 square vector, and we concatenate both as one long vector, which is 2 times 16 square by one vector. And that's our flattening. We are just implementing, let's say, only one layer of convolution. And then what we do is we basically pass these to, let's say, a softmax units of, let's say, 5 classes, and we actually connect all these to all of these. That's our fully connected layer. Let's say we connect all these, and this results basically y1, this results basically y2, this results basically y3, y4, y5, and these are our estimated values. These are our estimated values, and let's say the true vector is without hat. So our loss function, let's define the loss function, is basically let's say sum over all the values. Let's say I varies from 1 to 5, yi hat minus yi. Let's say that's our squared loss function, just to keep the thing simple. Now we pass an image, we apply 2 convolutional kernels. The 2 convolutional kernels, each kernel gives a response after nonlinearity. We can combine these 2 responses as a volume, no problem. So these 2 can be represented as a volume with just depth 2 or the number of channels 2. Then for each channel we apply the max pooling, and after pooling we actually flatten out our output, and we apply one fully connected layer, which is a softmax unit, which means the nonlinearity here is sigmoid or logistic sigmoid. So that's our example that we will carry on throughout for understanding of backpropagation. And if we are able to learn how the weight update happens and how backpropagation happens in this particular example, we will see that all these things can be extended to a much larger network. So next we actually see the low-level implementations of convolutions and poolings. Okay, so in this particular video, in this particular part of the video, we actually discuss the general architecture of convolutional neural network and the conventions, and we also look into an example that has only one convolutional layer, and that's a 30 that actually takes input as a 32 by 32 grayscale image, and has 2 convolutional kernels, 5 by 5 each, with the same padding. We uses ReLU nonlinearity for that layer, and then we apply max pooling with stride of 2 by 2 max pooling. And we saw that the result eventually, when we flattened out the result, that actually becomes 2 times 16 square by one vector, and then we have a softmax layer at the end for, let's say, 5 units of those. We will actually continue this example in our next part as well, where we will be actually going into the details of implementations of convolutions and max poolings. And the same example will be we will carry on the same example in our third part as well, in which we will actually be driving the back propagation through chain rule and all the details that are required for back propagation algorithm for convolutional neural networks. So hope to see you in the next part, where we will continue this example to drive the implementations of convolutions and max pooling.